Hello, welcome to the lecture on types of data and their distributions. This is ITE 1812, Mathematics for IT. Let's first look at the learning outcomes. By the end of this lesson, you should be able to classify a given data set either as continuous or discrete data, represent a distribution of data using a histogram, and represent the distribution of data using stem and leaf plot, and eventually represent distribution of data using frequency polygon. So we'll be discussing about these concepts during the lecture. To the introduction, so we talk about statistics and model building. So here, any natural phenomenon we can observe can be modeled by some type of data representation. So we should be able to describe what is visible and to try and explain what is observed, and eventually to use this knowledge to predict event. So from historical data, you will be looking at predicting any future outcomes. So this is when the data representations and statistics come into play. So let's first look at what we mean by modeling. So we are given with a real world problem, and it should be represented in a physical model. So what do we mean by a model? It's a theoretical explanation of the considered phenomenon under study. So a model can be usually expressed verbally at the beginning before building up any mathematical or numerical models. It can be expressed verbally. So then a model can be used for predictive purposes to make reasonable predictions of the future outcomes. So to do this, initially we have a verbal description of the model, but we need to convert that into a set of mathematical equations, a mathematical model. So this will help us determine the values of a specific variable in the model based on the knowledge of values assumed by another model variables. So this is what we try to do with future prediction. And modeling will help us in doing that. Right. So we begin with statistical methods. Now we introduce what do we mean by statistical methods from the very fundamental concepts. So what we refer to as statistical methods, they are useful in making decisions based on the analysis of data. The data may be gathered by using carefully designed experiments. So design of experiments will not be discussed in this class. Anyway, carefully designed and implemented experiments will help collecting reasonable data to build up a model. But the thing is, we cannot design experiment or design and conduct experiments to account for every possible incidence. We cannot do that. It is time consuming, resource consuming. We cannot cover all the possible scenarios. Because of that, there's always some uncertainty in experimental science. So our target is usually to minimize that uncertainty by collecting reasonable amount of data. So we try to design statistical methods to allow us to assess the degree of uncertainty present in our results. And we try to minimize that. We try to make our predictions as correct as possible. So that's our eventual goal. That's our expectation. So statistical methods broadly classified into three categories. We can identify descriptive statistics, inferential statistics, and model building. So we will discuss about these three categories. We first look at descriptive statistics. So this is the study of how data can be summarized effectively to describe important aspect of large data sets. So this is about representing data so that we can explore and understand some hidden patterns or descriptions within the data. So, but if you look at the raw data set, you would not be usually able to identify any of these patterns or extract any information. But for that, you need to go for certain techniques and methods. So we are getting started with descriptive statistics. So this may include collection, organization, presentation, and analysis of data in order to describe various features and characteristics of such data. So this could be in the form of graphical or computational, depending on the situation. And so this can be in a form of a chart or a table, and which can display the trend, proportions, maximum and minimum values, and so on and so forth. So another concept we identify as inferential statistics or statistical inference. So this is about making forecasts, estimates, or judgments about a large group from the smaller group of actually observed. So we try to make predictions, make inferences using a smaller group actually observed. So this is what we try to do in statistical. We move on further by introducing more formal terminology. So this time about data. So you deal with data all the time, but let's try to formally define and understand what is meant by data. So these are basically various types of information that we gather to understand various processes. So it can be in the form of numbers, words, measurements, observations, or even just descriptions of things. So later we will categorize data into different parts. So initially we can identify two main types. Those are quantitative data and qualitative data. So let's first look at what is meant by quantitative data. So this is anything that can be expressed as a numerical value. So there are things that we can express in numerical values. There are things that we cannot. All right. So numerical or quantitative data, we can identify two major types: discrete and continuous. So in figure 12.1, you see in this slide, it describes the differentiation between qualitative versus quantitative data. So quantitative is basically values that can be, or data that can be represented in numerical values, and it can be further categorized into discrete versus continuous. And qualitative data those cannot be represented in numerical values. For example, these could be descriptions or any classes. For example, here it was great fun, or it was beautiful, it was not good, and so on. So these kind of descriptions fall into the category of qualitative data. So we will have more examples later on. So now we try to identify the two main categories of quantitative data. So what is meant by discrete data? So they can only take specific numerical values, and they cannot take anything in between. In other words, it can be represented in integer values, not fractional values. For example, you can take a number of employees in a company, a number of children in a family, number of students in a university, and so on and so forth. So those are discrete data. And then you can define continuous data. So these are also numerical values. It can take any numerical value. That means integers as well as fractional numbers. So, for example, we can have weight, height, length, time, temperature, and so on. So these are all fall into the category of continuous quantitative data. Now, the other major category, that is qualitative data. So these are data that cannot be represented numerically. So it can be described in terms of some quality or categorization. So some examples would be skin complexion, hair color, type of car, favorite color, and so on. Right. So here we have an example. Some of the examples given here. So we can identify what data type they belong to. So first, mass of an object. So we can easily understand that this can be represented in a numerical value, and it is not discrete, it is continuous. It can have fractional values. And the second one is favorite cricket team. So we understand it cannot usually be indicated or represented in a numerical value. So this is a qualitative type of data. And the third one is price of pencil. It is also a numerical representable data type. So it is quantitative, but is it discrete or continuous? It is usually continuous, right? It can take values in between. Number 4 is distance from home to university. So once again, quantitative and continuous. Fifth one, day of the week, not numerical. That means it's qualitative data. Right, moving on further with the concepts, we will now introduce population and sample. So what is meant by the population in a data set? The set of data that consists of all possible or hypothetically possible observations of a process. So all the possible values, that is referred to as the population of the data set. And then if we take a part of it, we can call it a sample. So contains only a part of the observations. So in the diagram, figure 12.2, you have this graphical representation of the much larger population. You can get a smaller sample. So that is the difference between population and the sample. Now, we define the concept of a reasonable sample. So what do we mean by a reasonable sample? So when we have a larger data set, larger population, we need to select samples for analysis. So in order for this sample to be a reasonable one, there are a few characteristics that we should consider. They should be selected at random, and this sample should represent the population. So that's number 2. Then it should be large enough to provide accurate data. It cannot be too small. All right. So if the population has thousands of data, for example, data points, for example, if the sample size is less than 10, that might probably be not sufficient data points in the samples. It's the sample size is not big enough in that kind of a situation. So it should be large enough to represent and provide accurate representation of the population. So that's what we expect from a reasonable sample. And the results are proportional to the results of the population. So whatever analysis you do on the sample should be reflected and should be applicable to the population. So that's what we expect from a reasonable sample. And as the sample, a reasonable sample can be used to make predictions about the population. So that's what we usually expect from having a reasonable sample. Some examples here. To understand the population and the sample, so take, for example, all the students in a school, that can be the population, and you take specific class, that can be a sample of the total population. Similarly, all the books in a library can be the population. And then if you select certain number of books, let's say 10 books, that can be the sample. So these are some examples. Right, so we move on now to represent the distribution of data. So to how to identify, so how to get a clue about what kind of distribution that the data set belongs to. So the data distribution, usually they are characterized by certain factors, namely the central tendency, variation, and the distribution. Right. So to get an idea or to determine the distribution of data, we can use several techniques. So in this case, we introduce some of the graphical methods, namely histograms, stem and leaf plots, and frequency polygons. So we will take each by each and explain how they are generated. So first, taking histogram. So histogram is usually a set of rectangles, and these rectangles have certain features. Its width is proportional to the range of values within a class. So we define a rectangle for each and every class, and its height is proportional to the number of items falling in the class, or in other words, the frequency. And the class midpoints are represented in the horizontal axis, and the rectangles of the areas of the rectangle are proportional to the frequencies. So eventually, when you have the histogram, the shape of the histogram shows the shape of the distribution. So we will take soon an example to show that representation. So there can be three main types of distributions. The first one is symmetric or bell-shaped, and other two types can be skewed, either right skewed or left skewed. So let's in the next slide take some examples. So in the case where the histogram shows more than one clear peaks, in that case, we can assume that the data, it is not coming from a single distribution, it's probably a combination of two distributions. But in these examples, we don't see such an example. So the concentration of data can be seen with higher rectangles, because higher rectangles represent higher frequencies. More data points are represented there. So in the figure 12.3, what you see in this slide has firstly a symmetric distribution or a bell-shaped distribution, and then skewed distribution, skewed to the right. That's what you find in the middle. And another type of skewed distribution, skewed to the left, what you find on the rightmost graph. So that's about histograms. And we now take an example. So where you are given with a set of data, which has different class intervals, and the midpoint is also defined, and the frequencies of each class is also given. So how do you do these histograms? So you represent each class with a rectangle. So the frequency is represented on the y-axis. So for example, take the first class, the interval is from 15 to 25, the midpoint is 20, the frequency is 9. So you can see on the y-axis, the first rectangle represents 9 on the y-axis because the frequency is 9. Similarly, for all the other classes, you can draw a rectangle depending on the height. That means the frequency of each class. So this is how you develop or draw a histogram. And then the histogram will represent or give a clue about what kind of distribution the data represents. So in this case, we can see that it's a skewed distribution, not a symmetric one. So it can depend on the data set. The next one, this next representation is the frequency polygon. So this is a type of line chart of frequency distribution. And on the x-axis, the class midpoints are marked, and on the y-axis, against each class, midpoint of the relevant frequency. So the endpoints, how do you determine the endpoints? Joined to the x-axis. So you have two sides. At one class, width to the left from the first class midpoint. So that is the starting point. And one class width to right from the last class midpoint. So that's how you end the histogram, end the frequency polygon. So let's take an example. For the same data set, you can draw the frequency polygon. So once again, you have the class intervals 15 to 25, midpoint is 20, and on 20 you have the frequency 9, and 25 to 35, frequency is 13, you have the data point there, and so on. And you can have the starting point and end point based on the adjoining the classes. So the first class and the last class and the neighboring classes, taking the midpoint, you can get the starting point. Okay, so that's frequency polygon. So the next graphical representation is stem and leaf plot. So this is a special case. So this is only used if the first digit provides a good basis for separation of the data into groups. So the diagram uses the actual data values, and first digit would be the stem, and the rest of the digits would form the leaf. So this is how we draw the stem and leaf plot. So we'll take an example that will be more easier to understand. So draw the stem and leaf plot for the following data. So you are given a series of numbers. So the first step would be to arrange the data in the ascending order. So you arrange it, so you get 0, 2, 0, 6, 10, 20, 13, 24, and so on. So how do you select the stems? So in this case, we can select 0, 1, 2, 3 until 6 as the stems. So how do you form the leaves? So for 0, take the initial two values, you have 0, 2 and 0, 6. So when the stem is 0, leaves are 2 and 6. And when the stem is 1, the leaves would be 0 and 3. And when the stem is 2, you have 24 and 25. That means 24, 25, and 28. That means the leaves would be 4, 5, and 8. So here, leaves, when the stem is 2, leaves are 4, 5, and 8. So this is how you draw the stem and leaf plot. Right, with that, we come to the end of the lesson. So in this lesson, we discuss the basics of types of data and their distributions. In the next lesson, we will continue the talk on data and their distributions, specifically about tabular representation of data. Thank you for listening. See you in the next lesson.